Dan Gray, UCSD. That's okay. And he'll tell us about cosmological observables in flat space.
Okay, thanks for the invitation. So I'm going to talk about this paper that came out in December with a postdoc at UCSD, Glenn Ellison. I should qualify that Thomas encouraged me to talk about this paper, and I felt it was necessary to try to give some context for why I personally am interested in these topics and how they fit into other areas. But I think there's a chance it'll be a bit clunkier than a normal talk that I have given because I'm still figuring out how to put all those different ideas together. So I hope you'll bear with me, but I hope I can at least convey both the sort of flat space physics and cosmology and how they fit together at some level. Okay, so plan for my talk is first I'm going to just go over some aspects of QFT that show up in inflation and what kind of problems are relevant for understanding cosmology. Then we're going to talk about cosmic observables and their flat space counterparts. Then we're going to discuss how to think about effective field theory when you look at things like cosmological observables, and we'll focus specifically on how to think about things like wave functions and flat space. And then we'll bring this back to cosmology with some implications at the end. Okay, so quantum cosmology is a funny subject. I mean, people have been talking about it forever, and mostly it's just a list of questions with very few answers. So some obvious ones are, what does it mean to have a wave function for the whole universe if no one's outside to define what it means to observe it? There's, of course, then the question of what are the observables in cosmology? We don't have good answers to that. And we also don't know what happens when quantum fluctuations become large, like internal inflation, and you're trying to define what it means to do quantum cosmology when the metric is a very quantum object. And then to add to all of these questions, we have the more pragmatic question, which is, should we even care about this subject? The universe certainly seems classical for all practical cosmological observations. And so it's certainly, there's a group of cosmologists who would like to say that there's no reason to study any of these questions, and it is the subject for the philosophy department. Now, we basically haven't answered any of these, but I think I would like to argue that it is not the case that understanding quantum cosmology is not relevant for understanding our own universe. The reason is that we have very strong evidence that we have experienced or are experiencing two eras of accelerated expansion in the history of the universe, one at early times in the context of inflation, and of course today in the world of dark energy. When the universe undergoes accelerated expansion, due to the expansion of space-time, what starts as very quantum objects like the interacting vacuum can be turned into very classical density fluctuations. So just to give some specifics for sort of variable names and how this happens, in the context of cosmology, we're often thinking about the distance between points evolving in time according to a scale factor I'll call A of t. And in the context like inflation or today, that the rate at which points move apart is nearly exponential, and the time scale associated with that exponential is called h, which is the Hubble parameter. The Hubble parameter is also relevant for controlling the distance between points where you can actually exchange information efficiently. Once things are further apart than 1 over this Hubble parameter, things stop being able to exchange information, and causality dictates evolution in a very different way. So physics is described in accelerating cosmologies by the fact that points get redshifted to be very far apart, and very quickly those points are no longer able to communicate with each other. What this does is that it takes these quantum fluctuations, so we think of the consequence of this evolution mode by mode, it redshifts the wavelength, so it takes things that are short wavelength and redshifts them to long wavelength. And in the process, because of the presence of this horizon, that once they become very large compared to the horizon, they also become classical, and they behave like classical density fluctuations, not just quantum vacuum fluctuations. The canonical example of this is inflation. So in inflation, you've probably all seen this picture. We arrive at something like an exponentially expanding universe because the potential energy at the beginning of inflation when the scalar field's at the top of the potential, looks like potential energy domination, which means that the Hubble parameter is nearly constant. And then because it's a quantum mechanical object, the scalar field fluctuates at different points in space. And as a result, the amount of time that this scalar field stays at the top of the potential varies from location to location in space. And so this leads to these density fluctuations in the form of something that just looks like the amount of expansion varied from place to place in the universe. Since expansion dilutes energy densities, that also means that classically the total amount of energy density in any object is changing from place to place just because of the duration of inflation. Now, this picture, of course, is totally consistent with the fact that everything we observe today is classical. So certainly by the time all of inflation has happened, it's created these just very classical density fluctuations. We observe them in the forms of huge objects like stars, galaxies, clusters of galaxies, and nothing that we observe directly is inconsistent with the fact that these things were generated from a classical probability distribution. So to answer questions like what is the role of quantum mechanics or quantum field theory in understanding the universe, it's a slightly different problem than something like Bell's inequality, where you just directly interact with the quantum object. But that shifts the question in an interesting way, and there's interesting things to do just to understand the role of quantum mechanics. But it also has the benefit, there are benefits to the fact that it is classical, which is that the notion of that there should be observables, that there are things that are really that we can observe in these spacetimes is more straightforward because we do observe stuff. It is a very classical universe. So there must be some sanity checks on the kinds of questions we ask and what answers we should get when we ask those questions. Now, in practice, the way that we do this is we usually, instead of trying to think about the wave function of the entire universe all at once, typically what we do is we think about the wave function for the fluctuations around some classical background, and that generally makes answering a lot of these questions easier. And in the process, this is usually all we need to know in order to address observations. So this picture of balls rolling down hills with quantum fluctuations, as I said, that point of view of just thinking this is sufficient to understand observations. It's certainly a starting point for getting a handle on the universe. But just because the data is consistent with a simple picture doesn't mean that there cannot be much more complicated dynamics underlying what we see in the data. And so it is part of the program of cosmology to not just answer, is this one picture consistent with the data today, but what are the space of all the possibilities that are consistent today and could get different answers in the future. So one way we go about doing that is by expanding the definition of inflation beyond a ball rolling down a hill to try to put the minimum theoretical prior on what we think happened, and then ask questions about what could happen in that context. So within that point of view, it's typical to define inflation by these two fairly minimal conditions. The first is that inflation was a period of exponential expansion. That means that this parameter h was roughly constant. So that said precisely that the time derivative of the Hubble parameter is small in Hubble units. Now, pure de Sitter would satisfy this first condition, but would fail the second condition, which is that inflation has to end. So inflation is a finite period of time, and the end of inflation is a time in the universe. And so for that to be true, there has to be a physical clock. So in GR, we know that the times are only defined by what clocks measure. So if you want to define a time called the end of inflation, there must be some physical clock around to do that. And in the context of that ball rolling it down a hill, the role of the clock is played by the scalar field phi. So if you had a little detector that measures the local value of phi, you could set your clock during inflation by just measuring the local value of phi, and that would tell you some global definition of time during inflation. So this is often formalized in terms of the effective field theory of inflation, where the role of the clock is the clock is interpreted as some operator in a quantum field theory that acquires a time-dependent vacuum expectation value. Then we can think about fluctuations around this vacuum or this value by introducing a Goldstone boson that's associated with spontaneously breaking time translation. So we had something like a time translation symmetry. We broke it by the presence of this clock, and then it's restored nonlinearly through the presence of the Goldstone boson. And just like with ordinary Goldstone boson physics, we define some variable u that transforms linearly under the original symmetry. And then we can write whatever action we like for this theory, provided that we write it in terms of the variable u and derivatives thereof. And it will be invariant under the original symmetries of the problem, just non-linearly realized with the Goldstone boson. Now, of course, that's the statement if time translations was a global symmetry. Of course, gravity gauges time translations, and this Goldstone boson is eaten by the metric. And so we can instead choose a different gauge where we put all of the fluctuations in the metric in the form of this variable zeta, where zeta you can think of as just being the logarithmic change in the amount of expansion. So if I think of that A of t changing from place to place, zeta's written in that way, so it looks like a logarithmic change to A in different locations of space. It's just related to the Goldstone boson by a constant to leading order plus some small nonlinear corrections. Now, just like Goldstone bosons and massive gauge theories, there exists a decoupling limit where you can recover from the metric description a pure theory of the Goldstone boson. Because the Planck scale is dimensionful, the limit where you recover the theory of the Goldstone boson is to take m Planck to infinity, take the variation of this Hubble parameter to 0, such that m Planck squared h dot is held constant. This parameter here is related, it's proportional to the Goldstone boson decay constant, or the ion decay constant for this Goldstone boson. So this is the equivalent of sending g to 0, or g to 0, and m to 0 holding the ratio fixed to get f pi. Okay, so in this limit, you recover pure de Sitter space with a Goldstone boson, and this is actually sufficient to capture the behavior of the metric fluctuations up to small corrections because of some Goldstone boson equivalency. Okay, so just to summarize where we're at, we have a way to write a theory for a Goldstone boson. It's also related to the theory for the metric fluctuations, but for the context of most calculations, the Goldstone boson picture is sufficiently accurate to describe what's going on. So from that point of view, it's going to be useful just to think about what the scales are in this theory to get a handle on what we're learning from inflation. So these are kind of the relevant scales in the problem for inflation. So there's the Planck scale, which controls dynamical gravity. There's this Goldstone boson decay constant, which relates to the spontaneous breaking of time translations. This scale, in the context of slow roll, is just phi dot. It's how quickly the field is moving. Field was not moving in field space, then it would not break time translations. So how big this scale is tells you how the energy scale associated with how this symmetry is broken. At this scale, both time translations and boosts are broken. Then there's the scale Hubble. That's the scale that controls causality. It's also what sets the amplitude of the fluctuations produced during inflation. And then there's a scale h dot down below, which controls the fact that it's not quite in de Sitter space. Something we know for sure from this picture is that the ratio of these two scales is 59. So this is because the amplitude of metric fluctuations, as the variation of temperature fluctuations in the CMB, for example, is controlled by this ratio. So we've measured the delta t over t to be about 10 to the minus 4. And after taking the fourth root and multiplying by pi, that turns into 59. Okay, so if we take this, so that's what we learned from just the amplitude of fluctuations. There's more we can learn about this theory from their interactions. So we, of course, have this totally general function, but we can expand it out to get a bunch of nonlinear terms. These terms are normally organized in power, the leading power of pi. So there's terms that appear at order pi squared, pi cubed, pi to the fourth, and then with varying numbers of derivatives. We often, for the purpose of observations, focus on just the first few, because those are the things that lead to the measurements that are easiest to do. So for example, if we have a 3-point vertex in our effective theory, so here's an example of a 3-point vertex, it will lead to a 3-point function of temperature on the sky that has then been constrained by observations. If we think of this, again, this is an action for a Goldstone boson. So these terms have more derivatives. They're irrelevant operators, so they come with some energy scale downstairs, and measurements of these statistics put bounds on that energy scale. And so if you go to this picture, this is what the current bounds look like. they tell you that what we know that the scale that controls interactions is about 5 to 10 times Hubble, but we cannot rule out that it's still below the scale of f pi. And that's important because that simple picture of a ball rolling down a hill only works if the scale is actually well above f pi. And so that means that there's this currently still with what we know, this entire region of potentially very different dynamics looks very unlike a ball rolling down a hill that's consistent with current data, but would have much stronger interactions than that picture. Okay, so part of the reason I wanted to introduce this picture was to motivate the idea that understanding the physics at different scales is a very important problem for understanding inflation. So if you want to understand models of inflation, it's very helpful to understand what do different models tell you in terms of what scale do the interactions come in, how are these theories UV completed, what do they look like on this scale. A lot of that can be understood even if we take the flat space limit of this picture. So de Sitter space is really what's happening at h and below. Everything up here is happening in effectively flat space. And so you could just take the decoupling limit, take h to 0, and you're left with just this theory of a Goldstone boson in flat space, and you can study it just using the S matrix, for example. Or you can study it in flat space to get a handle on what's happening in this effective theory below the UV scale. So in this regard, there's a lot of value to be gained in understanding this theory without having to talk about cosmological backgrounds. This has actually been really useful in the context of the cosmological bootstrap. So I'll just highlight some things here. I won't talk about it in great detail. In the cosmological bootstrap, you can directly translate aspects about the scattering amplitude back into statements about cosmology. You can use aspects of the scattering amplitudes to construct soft theorems for this effective field theory. You can try to use the scattering to produce positivity bounds. Currently, a lot of this work is at tree level, but there's even some attempts to apply this kind of thinking all the way through to non-perturbative events. Okay, now my particular interest that I will try to highlight a little bit towards the end of the talk is understanding what happens at loop level. So a lot of what's happened so far with connecting amplitudes to cosmology has happened from trees, and just saying I have a tree level scattering, I can relate it to some tree level process in cosmology. Loops in cosmology has been a kind of long source of confusion. There's a lot of weird divergences that have not been well understood. This includes a bunch of technical issues like the fact that we don't know how to do dim reg effectively in these backgrounds. And even once we properly understand the divergences, the interpretation is subtle. And so a lot of what we're going to talk about today is trying to answer one step before, what would these things have looked like at the level of flat space? Okay, I'm going to pause there. That was a lightning inflation motivation. Was there anything, people with me so far? You can forget this if you don't like inflation. I'll take a poll at the end of who hates inflation at the end of the talk. Okay, so no, yep. Sorry, what was that?
And that also explains the inflation.
2D inflation, was that? So this gold, okay, so I think you're asking because there's no spontaneous symmetry breaking in less than 2D. So these Goldstone bosons will, in de Sitter, actually, there's that same argument applies to all D in de Sitter. So technically in de Sitter, all scalar fields will have the same kind of IR problems that a 2D scalar field does. So, so yeah, there's a sense in which if you're happy talking about approximate symmetry breaking in 2D over finite volumes, the same is kind of true for a finite period of inflation. We can come back to it. The answer is that a lot of understanding the IR divergences that happen at loops that I was alluding to here are related to exactly the questions of how do you think about physics in 2D. So there is actually a very close analogy, and I can try to bring it back at the end of the talk. But that's one of the, I can maybe talk to you afterwards. There's a very precise connection between 2D and some of these issues. Okay, so I want to kind of dig in a little bit more on what the observables in cosmology are, because I want to construct those in flat space and talk about what they mean in flat space. So in practice in cosmology, we make maps So on the left is a map of temperature on the sky. On the map is on the right is the map of galaxies as a function of redshift and distance, angle and redshift, which is turned into three-dimensional positions. Now these are just maps. We then assume that these maps were generated from a probability distribution that was homogeneous and isotropic in order to convert the information on the maps into statistical quantities. So if we assume, for example, that the thing is homogeneous, then if I construct, say, take 3 points and or it's isotropic and take 3 points on the sky, and I just take those values and I multiply them, and then I average over all other triangles that are the same size and shape, just different positions in the universe. That average, if I make this assumption, will eventually should converge to the statistical average from whatever probability distribution they came from. This is the ergodic theorem that, again, assuming homogeneity tells you that averages over space is the same as statistical averages. So this is a core assumption. Now, this average here is, for all practical purposes, a classical statistical quantity because the late universe is classical. Quantum mechanics does not matter. It's irrelevant in the technical sense. The basic reason is that because of causality and the equivalence principle, any commutator you try to form from anything you can observe ends up having to be, you're almost always observing equal time quantities. So all the commutators can only be delta functions, and then they have to be suppressed by the volume of the universe to be invariant under diffeomorphisms. And so all the commutators vanish when the universe becomes big. This practical fact means that for whatever cosmic observable I care about, I just have some initial condition piece plus purely classical evolution. So whatever map I take, I'm taking some initial condition in terms of the scalar metric fluctuations that I compute, say, during inflation, and then I'm just evolving it forward with some classical transfer functions. So when we measure, say, map the statistical correlators of density, that's the same as what I'm going to explain here, which is called an in-in correlator of the metric fluctuation during inflation times a bunch of transfer functions that we don't care about. Here I'm going to consistently work in momentum space because inflation is usually best described with a bunch of flat slicing so that it has translations in the spatial coordinates. And when you have nice translation invariance, it's the nice Fourier transform. Now this in-in correlator here, you can think of non-perturbatively as the following quantity. It's just like calculating an average in quantum mechanics in the position basis. So if I want to calculate this endpoint function here, I would just take the absolute value of the wave function squared in the position basis, multiply by whatever functions I'm interested in, and then integrate in order to compute the statistical average. So all the quantities we're calculating as a non-perturbative level are just this object. Now in practice, we typically don't calculate some people calculate the wave function as an intermediate step. Other times we can skip straight to the final answer using an interaction picture description. So when you calculate an in-in correlator, you're using an interaction picture to evolve from t equals minus infinity on both the left and the right, but you have slightly different I epsilon prescriptions on the left and the right to ensure that you're in the correct interacting vacuum. This is very similar to an in-out correlator, except that you have this different I epsilon prescription on both sides. So to be specific, this is what the contours look like for time for an in-in versus an in-out correlator. So on the left, this purple-looking curve is what an in-in correlator is. We come in from minus infinity plus I infinity, and then we put all of our operators at a specific time. Let's call it t there. So my operator q of t is whatever object I'm trying to measure. It's some equal time correlator. The upper branch here is defining the wave function. Then the path goes out to minus infinity minus I epsilon, and that's defining the complex conjugate of the wave function. This we should contrast with an in-out correlator, which is some correlator defined as minus infinity to plus infinity with just one I epsilon. And here we might locate the operators at different points along the contour. Now you can see that if I analytically continue the bottom curve to the right, there's not a huge difference between the in and the in-out correlator, and that will also partially explain why we'll see so many connections between S matrix elements, which are related to the in-out, and in correlators, which are related to these cosmological observables. So here's a simple example. Let's just say we take one of those terms in the EFT of inflation. I picked this one because the answer takes the fewest, the least space to write down on the screen. But here is a simple 3-point vertex. We would calculate it at leading order using this interaction picture just by taking the commutator of the interacting Hamiltonian with the fields defined here at conformal time equals 0. I then do this integral, analytically continuing to deal with the vacuum, and I get this following answer. The thing to notice about these answers is that they almost always have this structure of a thing that we'll call a total energy pool. Here, the reason it's called total energy is because these are massless fields. The energy is the length of the momentum. So K1 here with no arrow on top is the length of the vector. And so this thing looks like the sums of the energies of the 3 fields that you're trying to measure. So specifically, the meaning of this total energy pole you should think of as being the cosmological equivalent of the energy conserving delta function for some scattering process. So here what we're doing is we're creating 3 particles from the vacuum. So that should have been forbidden by energy conservation. But of course, there is no time translation symmetry in this problem. We're not evolving it forever. And so instead, we're just paying an uncertainty principal cost. So it's suppressed by how much energy I have to borrow from the universe to create these 3 particles, but it's not 0 because I've broken time translations. So this is what we get from vacuum fluctuations producing, say, 3-point statistics. But this pattern is not just an analogy, this is actually precise. So one can show that if you analytically continue to the location of this pole, the residue of that pole can be written as the on-shell scattering amplitude for that 0 to 3 process. Okay, when you analytically continue, that becomes something like a 1 to 2 process, so that it conserves energy. But so there is a precise sense in which this is not just kind of like the energy moment conserving delta function of a scattering amplitude. It is literally the energy conserving delta function. And then the stuff upstairs is what contains all of the interesting dynamics that control the actual amplitude. Now, you could try the same thing and you could with some theory that was not in the vacuum. So you could just say, hey, what if I generate a 3-point function from a classical system with nonlinear time evolution? So you could take roughly the same setup and you could just do perturbative solutions to equations of motion and get a very similar looking structure, except that in addition to the total energy pole, you'll get poles that are accessible on shell. These extra poles correspond to physically producing or physically decaying or producing particles. So that's why you have things that you can actually reach, because this is a really physically loud process. So if I start in a system with actual particles and not in the vacuum, then I can have, say, 1 particle decay to 2 other particles and an antiparticle. And this will produce my 3-point function. Now, of course, by crossing symmetry, we expect if you have the 0 to 3 process, you should have all of the processes there. And of course, all of them are allowed. But what happens is that when we're in the vacuum in quantum mechanics, you don't have these other processes because there's no particles in the initial state. So quantum correlators in de Sitter only exhibit the total energy pole and not these other poles. But that's an indication of quantum mechanics of the interacting vacuum and not anything to do with the dynamics of the theory. Now, this is an important tool when trying to understand the cosmological bootstrap, because exactly this physics, specifically the absence of additional poles, plus the statement that the residue of the total energy pole is the scattering amplitude, is how people are able to take the scattering amplitudes in flat space and analytically continue them to construct full cosmological correlators. So we can construct the full in-M correlator if we know this structure, this analytic structure of the poles and the flat space scattering amplitudes. Now, there's a number of scattering amplitude people in the audience, so I'm going to address the one possible confusion about this object. So occasionally people bug me about in correlators and they say they're not invariant under Fielder definitions. So what are we talking about? Specifically, if I measure, say, if I have a generic scalar field and I measure a 3-point in correlator, or I do a Fielder definition so that this is some arbitrary function of this scalar field, the in correlators are not the same. And so that might make you worry that the whole subject is ambiguous because there's no invariant definition of the object you're calculating. There's two reasons that this doesn't bother us so much. The first is that these total energy poles can never be produced by Fielder definitions. So of course, as you expect, the residue is the S matrix. So the structure of things on the total energy poles is totally fixed by the S matrix and is not changed by Fielder definitions. Again, as you'd expect, it's related to the S matrix. And then the second thing is that a bunch of these operators we care about, like the scalar metric fluctuations, are completely fixed by symmetries. So once you specify how these operators transform under symmetries, so for example, for the scalar metric fluctuation, it transforms nonlinearly under a coordinate transformation. Once you specify that the object you're measuring transforms according to this rule, there's no way to make a Fielder definition that preserves the transformation under symmetries. So again, you should, for those familiar with CFTs, you just think of this the same way we think about why it's useful to organize CFTs by operators and correlators, even though the correlation functions are not invariant under Fielder definitions. You first specify how they transform under the conformal group, and then you define the correlators. Okay, so everything I've talked about so far, you can do equally well in flat space. So I could just take a generic 3-point interaction, some scalar field. I could calculate an in correlator in flat space. It's the same formula, just removing the A of t and just having a time integral. And you'll see exactly the same structure. So the only thing that differed from the previous slide was the powers of k that appear downstairs here, but you still have the total energy pole for the same reasons as before. Now, that sounds confusing at first because in flat space, you don't have spontaneous creation of particles. And so you would say, well, why would I interpret this non-zero answer for a flat space in correlator as particle production and not in a cosmological background? And the answer is that what you should interpret this 3-point function as doing is it's related to the amplitude for exciting 3 particle detectors that measure the local value of phi. So specifically, I can create a model of a detector that responds to the value of phi. There's some, I have to introduce these functions that localize the detector. So I have to say this detector is a specific region of space and time, and it's the presence of localizing the function in time that breaks time translation, right? I have to say the detectors here are not there. I have to say the detector's only turned on for a small amount of time, so I can resolve the time that will measure the correlator. And all of these functions are responsible for being able to create particles from the vacuum. So if you widen if you take the width of this time resolution to be very wide, you don't get this formula here. Here, I'm really assuming that I can measure perfect accuracy in time, which puts in an infinite amount of energy by the uncertainty principle. And then there's some state here which excites, let's say, a 2-level system to tell you whether you did or did not detect a particle. And the amplitude for exciting that thing is proportional to the in correlator. So here, the in correlator, when you think about physical observables, there's nothing surprising about this fact that you create the particles. You're just putting in the energy when you create the detector. Okay, so this is going to be the background for what we're going to talk about. We're going to talk about how to think about these kinds of objects in flat space. Again, with the understanding that when you get confusing answers, you should always go back to this picture that it's physical particle detectors and energy is not conserved because you're putting energy into the system through the detector. Everyone with me so far? Okay. Okay, so one of the reasons that, just to bring back to what we were talking about before, is that one of the things we're trying to understand is how to think about these objects at loop level. So in the context of cosmology, when we calculate loops, we get all kinds of funny divergences. So we get these things that are called, this is called secular growth. It's the log that grows with time, so it diverges as t goes to infinity. There are also IR divergences. These are just diagrams that are infinity as p goes to 0. In NED is particularly the problem. Now, it's generally believed, and there's a lot of evidence for this now, that the resolution to all these problems is to treat these logs as using RGFlow. But this is something we want to understand better, and that's kind of why we're looking at flat space in this context. So specifically, the idea is, let's say, rather than thinking of A of t times h as a time, and this being some kind of time-dependent log, think of A of t times h as just being the UV cutoff of some effective field theory, and this is just a conventional log of the scale over the UV cutoff. And then if you find these kinds of logs, you could resum them according to RG. So in some simple example of calculating a 2-point function where you find this kind of log, you should interpret the coefficient of this log as an anomalous dimension and resum the whole thing to get what you would expect, which is the total dimension of the 2-point function. Now, there's a lot of indirect evidence that this is the right thing to do every time you see one of these kinds of logs. But one of the things you would like to do is to be able to prove that this is always the correct thing to do, the same way we know that that's the right thing to do in flat space. We don't have a lot of confusion about how to deal with, say, anomalous dimensions in the context of perturbation theory in flat space. So flat space is the strongest piece of evidence for the sort of nicest conceptual picture of why we do what we do with RGFlow comes back to thinking about exact RG, the way that Polchinski taught us. So the idea here is that by thinking about the full partition function, you can write an equation that says all of the information that's encoded in in integrating out a shell momentum can be reabsorbed into the action. And in fact, it's not just, it's precisely these two diagrams that contain all the relevant information. And so in this way, we could just directly show that there's no evolution that comes from integrating out a shell momentum that's not absorbable back into the action. Now, the question we want to ask, is there any subtlety? So this is done for, say, a Euclidean partition function. Is there any subtlety in integrating out a shell of momentum when talking about an in correlator that would make you think that we can't just straight out of the box apply Polchinski to de Sitter space? So the challenge, just in pictorially, the issue is the following. So when we think about absorbing things into the action, we're not normally thinking about this contour that sort of has two different real times, but they're different parts of the complex plane. So we have the time associated with the wave function, the time associated with the wave function squared, but we have Green's functions that allow information to go from the top to the bottom. So for example, there's a diagram that's like the exchange of an interaction. There's an interaction vertex on the top, interaction vertex on the bottom, and we might want to integrate out the momentum that exchanges this information. But that wouldn't necessarily look like a local term in the action, because a local action should separate into a part that lives on the top part, a part that lives on the bottom part, whereas integrating out something that communicates between the two would generate some kind of mixed function of t and t plus and t minus, the top and bottom of this contour. Usually when that kind of term arises, that's associated with dissipation. So for example, in Feynman-Vernon, a whole way of organizing dissipative systems that morally boils down to allowing for interactions between the top and bottom of the top and bottom parts of this contour. Okay, so this is sort of the most obvious thing we have to deal with if we want to understand if there's any new complications of thinking about EFT for in correlators that we wouldn't have seen at the level of the Euclidean partition function. So since all we're really worrying about is this tree level exchange, that's the diagram in Polchinski, this equation from Polchinski that we're most worried about, we can actually understand most of this problem without even calculating a loop, but just by thinking about trying to integrate out the exchange of a massive particle. So here we're just going to think about an in correlator of a light field phi interacting with a cubic vertex through a heavy field sigma. And our goal is to ask, to what degree can we integrate out the field sigma to recover the correct in correlators of the field phi? Now, if we were calculating the S matrix, we could just complete the square and integrate out sigma to get the following effective 4-particle vertex. And of course, then we could expand in the derivatives being much smaller than m to get an infinite series of terms. Now, of course, we know the UV theory, so we could also just go and calculate the full in correlators in the UV theory and ask what happens when we try to take the m to infinity limit to recover the answer of that you'd expect of the EFT. So the first thing you'll notice is that the 3-point in correlator involving the light fields and the two light fields and the heavy field does not go to 0. It's still non-zero, but it's still non-zero even if the momentum goes to 0 compared to the mass. Now, again, it depends if you want to call the energy 0 or just m, but it's still present at some level. It's not exponentially small, and usually the stuff we integrate out is supposed to be exponentially small. The second issue is that the 4-point vertex just has terms that would not be there if you only use the EFT. So the easiest way to see that is, so this E here is the square root of m squared plus k squared. So it's the energy associated with the extra particle. Now, if you just Taylor series this thing at m, you will find in particular that there are odd powers of m that show up in the answer. So odd power, so we know that our usual EFT answer has only even powers of m as you expand in derivatives. So any odd powers of m are sort of an obvious signal that there were terms that you missed when you just used the effective action. Okay, now it's possible to just guess a term you could add to the action that would fix the answer. So this term, if you guess it, does reproduce the full answer. In this case, it's a boundary term that's localized only at the time of the observable. So that's the first funny thing. It's just a boundary term in the action. The second funny thing is these i's. These i's should make you unhappy, and we'll come back to figure out what to do with those i's and why they're there in a second. The important thing is that there's sort of, even this term splits into two different parts. So there's a bunch of terms that are even in m, and those arise from just demanding that the theory has a well-defined variational principle. So there's a boundary time t, and if I want to vary the action and be able to define a set of equations of motion, I have to add a few boundary terms at t in order to cancel the integration by parts terms. And those are fine, and you could predict those, and they explain the even powers of m that appear in this expression. The odd powers are okay. They generate semi-local terms than the correlators, but they have less of an obvious interpretation. So the way to think about this is as follows. So remember, the definition of the in correlator was, in the full description, was that we could think of this as the wave function squared. It gives us a probability distribution, and the correlator is integrating the fields over the probability distribution. And then each one of these wave functions was like 1/2 of this contour integral. So in this case, this was the top half is the wave function. Now, when we want to integrate out sigma, we really don't have we started with a wave function that had two fields, phi and sigma, and now we want to integrate over sigma. But we really want to integrate over sigma at this level, where we trace over the wave functions in the density matrix to arrive at a reduced density matrix. Okay, that's also apparent because we had a non-zero correlator between sigma and phi, and so we can't just remove phi from the theory entirely. It is still correlated with the field, so instead we should trace over it and recover a reduced density matrix for phi. And so one of the reasons it's confusing that we don't have a local action that explains the theory is because we no longer, the local action would just give us a wave function. We could use it to calculate a wave function. And the point is that after we integrate sigma out, we don't have a wave function anymore. We have a density matrix. Now we can see that explicitly if we were to go and try to write our answer starting by defining a wave function. So we just Taylor expand the wave function, the log of the wave, or we just expand the wave function in powers of fields times wave function coefficients. Then this 4-point function we calculated in terms of the UV wave function is related to the 4-point wave function coefficient in the UV theory times the product of the 3-point wave function vertices, including this extra field. Now here I've written it this way. In actual fact, this is the sum of 4 terms that include the multiplication of the wave function coefficient times its complex conjugate, which means that they came from opposite sides. One came from the wave function, one came from the wave function's complex conjugate. So these terms in particular don't exist at the level of the wave function. They come directly from integrating out, from tracing over the wave function. The reason I've written it this way is it just so happens that all these terms are real, and so they're all the same number. But in fact, it's important that 2 of these terms could not have been generated just from the original wave function. So pictorially, the terms we're missing are these ones. So here we have, if we think of sort of the diagram is split into the parts of the diagram that have t plus and t minus, those 4 terms can be written in this way, and we see we have these 2 terms involved across a diagram that lives at plus t plus, a diagram that lives at t minus, and then the exchange of this heavy field between those 2 times. This is a different way of saying this is the heavy field is entangled with the light field. And so when we go to measure the light field correlators, we're missing the information in the production of the heavy field. And so we have to trace it out to get a density matrix. Now, these terms are all semi-local, as in they look like delta functions. So if you were to again think of the picture of detectors, you'd actually only pick this up when 2 of the detectors are placed on top of each other. And that's, of course, because this field doesn't propagate. The heavy field doesn't go anywhere in the amount of time between when it's produced and when you detect the particle. It's just sitting there at rest. So we're not missing terms that we're deeply concerned about. They're still delta functions. So if you're the kind of person who thinks all delta functions are incalculable and you should have never worried about them anyway, you would have never worried about these issues. But there is some interesting physics encoded in the fact that we don't directly reproduce the UV and the full UV and correlator just from the effective action. Okay, so this example of the heavy field is just what happens in general. We can go through the same argument from Polchinski, just updated for this contour to see that these extra terms arise from exactly this effect of having terms at different times. So again, you could do the same thing as Polchinski. You can define a full partition function. In this case, we're defining some kind of partition function for the in correlator with some kind of UV regulator defined by a kernel as a cutoff lambda naught. We can then integrate out shells of momentum to get down to some effective UV cutoff, which is lower than the original UV cutoff, presumably at the cost of changing the form of the partition function. And we're hoping that we can absorb all of the changes by just changing the effective action, but we've added the possibility of some local term that lives only at the time we make the measurement. Now, of course, we can then just go through and ask how much does the partition function change as we change the cutoff, and that gives us this kind of seemingly boring equation. But of course, we know that nothing should depend on the value of this cutoff because it's artificial, we're just integrating out, and so this equation should be 0. And the question just boils down to, can we define the change to the action such that this whole expression is 0? Now, this is the same thing as calculating momentum space entanglement. We're integrating out a shell momentum. This entire setup was already described about 13 or 14 years ago in this paper on the relationship between partition functions and density matrices. So we're not covering entirely new ground here. What we're trying to do is give both the consequences of momentum space entanglement and how we think about cosmological correlators, and hopefully also give a better physical interpretation of why there's a density matrix here and why we never worry about this density matrix when we're doing other calculations. Okay, so for all practical purposes, this looks just like exact RG, with the only subtlety that we're defining things on this funny contour that comes in and goes out. So we could, of course, do everything exactly the same as long as we're just careful to define the Green's functions that live in this expression as the path order Green's functions along this contour. So the key steps are not particularly difficult, they're slightly technical. The key insight is just number one, that you can rewrite the change with scale of the quadratic action as just being related to two derivatives of the quadratic action times the Green's function. This is just a definition of the Green's function in action. And then you just use Springer-Dyson equations to integrate by parts until this looks like something you like. And so you get something that looks like this. You get that after integrating by parts, that the change of the interacting part of the action minus all of this stuff has to add up to 0, or said differently, we'll simply define the change of the action to absorb these two terms. Now, these are, of course, not local, manifestly and clearly integrating over two time variables in these integrals. But if these Green's functions are all exponentially small, or all vanish exponentially in the separation of times, we'll recover a local action after integrating. Now here we see the exact thing we were worrying about from the beginning. So this equation here can be pictorially represented as the following way. It says the change in the interacting Hamiltonian or the interacting action is just one term where you take the term and you close off one loop by gluing together two values of the fields, and another where you take two different copies of the interacting Hamiltonian and glue them together with one tree level exchange. The term on the right here is always manifestly local if the things are exponentially small. So this is just always absorbed into the effective action. And the only new term you have to worry about is this term where the times of these two terms correspond to different parts, one on the top and one on the bottom. Okay. Now, the reason that this is particularly complicated is because we still have this source term that we've added that lives between the top and the bottom. And so if this quantity doesn't commute with the source, we can't commute this thing past our source to write this as a local term. So as a concrete example, we could arrive at a situation where the term we want to add to the action is the following. It's say a time derivative on the upper branch, a time derivative on the bottom branch, and these things are approaching the time t0 where we insert the operator. But when you go to add this to a correlator, if we were to insert this, because of the time ordering, the term on the left here has to end to the left of the operator, the term on the right has to end to the right of the operator, and this structure is necessary to arrive at the correct answer. Okay, so these kinds of terms with time derivatives are specifically all the terms that are new and interesting that arise in this way, but also it's always the case that these things are semi-local. So here, notice that we got only two momenta downstairs. So there are four momenta in the problem, and it's analytic in two of the four momenta. And so this thing is some semi-local term, and it corresponds to some delta functions. Okay. The other thing to notice is in examples like this one, and all examples of this kind where there's interesting time derivatives in these boundary terms, is that it comes with an odd number of powers of a mass scale, which is exactly what we saw before. These are these kinds of funny terms, the odd powers of mass, that we needed to add in some funny way with some funny i's and time derivatives to reproduce the answer. So this is what's going on. These are new terms. They do not correspond to a local action, but they do just change contact terms. They don't generate any non-trivial long distance correlations. Okay, but any questions on this part? You look bothered.
Well, not so much bothered, just maybe you seem to have some physical interpretation for these semi-local terms in terms of the detector creating something heavy.
Okay, so if we go back to the correlation between phi squared and sigma, that's like where that correlator would be if you put the detector of the sigma on top. Here, let me go back to that expression. So go back here, okay? So now if we take m to be large, this expression will become analytic in K1 plus K2. It'll just become it. What will happen is that this will only correspond to when the detectors are all sitting on top of each other. So that it's like this will you'll get a delta function in one of the positions of the particles, so that you either have sigma on top of one of them, and then so it's like you produce a sigma and a phi together, and then the other one's correlated through the 2-point function, or vice versa. But so that's the interpretation of this local term, is that like you're putting in the energy to your detector. You have a little sigma detector, which is inserting an infinite amount of energy to resolve the time, because you're saying it's at t0 and not even epsilon away from that. So that inserts a lot of energy. So I produce a particle at that time that has a huge amount of energy, but of course can't go anywhere. So my detector only can detect it. I don't have any time for the other particles to propagate. So I don't have any non-zero distance between the sigma detector and the phi detector that are produced in pairs. Do you see what I mean? So that's why these things are always local, is just that like the detector is the only reason that you can violate anything that looks like EFT at all, right? Like the only reason you have to account for sigma at all is because of the role of the detector, but because the detector is infinitely localized in time, the ability for the effects of introducing that energy to propagate through the system are also localized in the time you reach it. And so you just like your violations of EFT intuition are all just localized at one point. Do you see what I mean?
Yeah, but you're allowing yourself to still have an infinitely sharp detector even in the EFT.
So, well, okay, so the other resolution would be to then not allow yourself to define these observables and insist that observables are smeared in time. And so that would be another strategy, but the challenge is that introduces a whole separate issue for defining wave functions, right? Because the wave functions are defined at a specific time. So you have to just say, what do I mean by smearing out in time the wave function? Because so just at the level of the partition function I wrote down, that is a statement of the wave function, which is defined at t and not t plus or minus epsilon. So you could try another strategy, which is again to say I only talk about observables whose resolution in energy is like I smear them in time so that they cannot probe these extra particles, and you'll indeed find that they start exponentially suppressing things. Because you put it like you can just imagine doing these integrals where I put a width, I replace this with, instead of a delta function, I put some Gaussian width here, and you'll start to see exponentials that relate to the width of that Gaussian field, and that Gaussian distribution. So that's how you would try to resolve these, but the problem is for quantities like the wave function, is just the wave function, it's already built in that it wants to be defined at a specific time and not smeared in time. You see what I mean?
But do you ever need the more fine-grained information?
Do I ever need the more fine-grained information? So here, if your question is, I mean, the answer is, I'll come back to it in the context of cosmology. Maybe that'll make it more clear. So the answer is in cosmology, no, up to one small technical statement. And in here, it's more the like, I'll tell you why you want to do this in a second. Yeah.
This example, isn't it a method when you double the degrees of freedom?
Yeah, so if you double the degrees of freedom, have degrees of freedom on the top and degrees of freedom that lived on the bottom. And in fact, that's in our paper, you'll see that integrating out sigma generates mixing between the two degrees of freedom.
Yeah, but you get the right formula there.
Yeah, you'll be left with a density matrix that includes the mixing of those terms. So that is precisely will generate. So indeed, you'll just generate terms in the density matrix that pick up this term. But they're not representable by a wave function because they mix the two sides. So your density matrix has all this information in it, but it indeed has the fact that it's not a pure state as well.
Let me ask a variant of my question, which doesn't make it seem like a choice. Well, roughly speaking, if you're a person who hates delta functions and thinks you should throw them away, then you should have the opposite. You should have a reason to keep them. So if there's some kind of
Totally fair.
Equation of motion or Schwinger-Dirichlet or something that forces you to have these delta functions, even though they look formally like they're a very short distance thing.
So okay, I think maybe I can come back to why. Maybe let me go to the cosmology part, because again, this was a warm-up problem for a cosmology problem. And maybe it'll make more sense why I care about this, because indeed you're right. There's not like in this context, you would just say, yes, but I never measure these things. There's no observable that a real human being will make that will be sensitive to these terms. And the whole reason you're confused is because you're calculating things that were not closely related to physical observables, right? And so really the lesson here is indeed, if you are not a fan of EFT, you might have landed on this calculation and said, aha, I knew EFT was always a lie and that there's violations of EFT all around us. And I'm certainly not advocating that at all. Instead of saying the way to resolve the confusion of the EFT, you have to think harder about what the observable is. Right? You really have to think about the detector and the resolution and time of the detector, because again, this is a thing I calculate. I just doesn't seem on its face that dangerous. And what I'm trying to tie it back to is precisely what thing that we measure that led to this problem. So the role of the detector is 100% of the reason we saw anything that required required beyond EFT thinking. So yes, it's totally UV, and the reason it's totally UV is because my detector put in an infinite amount of energy. But so the other thing I would add is the other reason these are semi-local is I can do all of that while still maintaining the cutoff in momentum. So I never put in an infinite amount of momentum, just energy, right? Because I look less in time, but I can still demand that my detectors, it's very easy to demand that detectors don't violate the cutoff in the momentum. It's really that the time and momentum cutoffs are different because I've broken the lens invariance with the detectors. Okay, I know I'm running a little bit short on time, so let me just jump, maybe I'll get to just the punchline for cosmology. Okay, so
Too pressure to be hyper on time. I mean, as long as you don't go for another hour.
I think I have 5 minutes. We'll see how, okay, maybe I can try to cover everything in 5 minutes. So, okay, so coming back, to put this back in the context of cosmology. Okay, cosmology, again, we observe we try to measure these 3-point functions. We usually talk about these 3-point functions in terms of a bispectrum, which is just a fancy name for the part of the 3-point function that doesn't have momentum in it. Now, because of symmetries of cosmology, we know that we can think of this as being an object defined on closed triangles, because the sum of the 3 momenta has to be 0. But also, in cosmology, things are approximately scale invariant, so we also don't think it depends on the size of the triangle, just the shape. And so when people talk about cosmology and these 3-point functions, they often talk about a shape and an amplitude. And this shape function has a nice inner product on it. So two shapes can be defined as being totally distinguishable if they have an inner product that's 0, so that they're orthogonal in some kind of sense. And so it's typically the case that we have this space of possible shapes, and we think about which ones have strong overlap. Now, the way that we think about the measurements of shapes is, so here's an example of a constraint on a 2-parameter space in the EFT of inflation. You should really think of this space as these different shapes as distinguishing different operators in the EFT of inflation. So just to give a sense of some of the shapes people talk about, so there's the local shape that's peaked in triangles where one of the sides is squashed. There's the equilateral shape, which is brightly named for shapes where it's peaked in where all the momenta are roughly the same size. And then there's the orthogonal shape that's kind of peaked in squashed and equilateral triangles. Now, the physics of these shapes is different. There's the equilateral typically tells you about self-interactions. There's the ones that are squashed typically tells you about these like poles of producing physical particles. And often particle production is associated with things that have a large squash shape. And then local terms tend to generate local non-Gaussianity, which is this squeezed triangle. Now, the worry you would have is that we've been talking about these extra terms that we were missing that look like delta functions, but in Fourier space, some of these terms will look just like these local terms in the action. So if you're saying, well, we're measuring all these correlators, and these correlators are indeed sensitive to just like seemingly analytic functions of momentum, then doesn't that change our ability to understand the EFT? Well, there's sort of 2 reasons that the answer is no. The first is that the terms that are really new that we talked about in flat space correspond to time derivatives. And in inflation, things that are proportional to time derivatives vanish with the expansion of the universe. They just redshift away, things become time independent. And so even if we add these terms to the wave function of the universe for inflation, they won't survive until we need the initial conditions. The second reason is that the origin of these terms with these detectors that we're injecting energy, cosmology, of course, there are no detectors because the universe is really just expanding at some rate h. And so physics way above h should not just have these direct production effects. They can be produced, but Boltzmann suppressed because h is more like a temperature. But the point is that these kinds of terms just go away because they're not actually being physically produced in the same way as the flat space detectors. So there are still terms with no derivatives that are left around. Those look like local fielder definitions. Now, these are forbidden by symmetries in single field inflation, but they're completely allowed in multi-field inflation. And in fact, multi-field inflation generically generates non-Gaussianity that just looks like a bunch of local terms. So the search, in fact, the search for local non-Gaussianity is often characterized as the method to tell multi-field and single field inflation apart. So there's a word identity says there's all this local junk has to be 0 in single field inflation, and otherwise it's just junk that we can't even really compute and we just go and measure, but at least it tells us how many degrees of freedom are in the problem. Okay, so quickly just some future directions. Okay, so first there's just this, we're still learning about this relationship between flat space and cosmological correlators. The S matrix calculations are very helpful. They've already been really useful in the Bootstrap. Places where there's still room for a lot of improvement is that, again, in the context of EFT inflation, we usually don't have sometimes not time translations, definitely we don't have boosts. And so understanding amplitudes in non-Lorentz invariant systems would be very useful. Same for things like positivity bounds that are useful for classifying EFTs. Those are quite a bit different when you don't have boosts. And then, of course, a lot of this structure at loop level is not very well understood. There's also a lot of interesting work to be done on connecting soft theorems that play a huge role in cosmology. I haven't talked that much about it, so I'll skip it. But the last thing I wanted to sort of highlight, which was why we were doing this in the first place, was that a lot of our goal was to use this Polchinski style argument to understand how to resum logs in cosmology in all possible contexts. So it provides us a sort of non-perturbative framework in order to understand the role of RG in cosmology, but we hadn't even solved the problem in flat space first. So flat space is a warm-up problem to understand what's going to happen. What we want to do is do this in de Sitter space. In general, we expect, I think there's an anomalous log there. We're expecting to recover RG-like equation for the full density matrix, which is what we found already. The reason that this looks like time evolution and not the cutoff is because what happens, of course, in cosmology is that physical scales evolve with time. So RG and time evolution become intimately connected. And so the non-trivial step from flat space to cosmology is turning both time evolution and RG into one object that then operates directly on the full density matrix. We already know that equations like this should be true for the trace of the density matrix. This is called stochastic inflation, has been proven very successful. But in general, we'd like to prove that approach of doing renormalization in cosmology is the right answer and is always the way to deal with logs, the way that we already do that in de Sitter space. And in general, this should also apply to ADS. A lot of some similar things were already noticed in ADS. The need for extra boundary terms when integrating out the holographic RG was noticed in some examples there. But again, I imagine that one could fully show that that's a generic outcome in ADS. Okay, so to summarize, hopefully I've convinced you that there's some interesting questions that are relevant to cosmology that can be answered by just thinking about physics in flat space. There's a lot of physics of effective field theory and RG that involves really putting in local observables to make sense of what's going on. This, I think, is an interesting comparison with what's been going on in the studies of quantum gravity, where people have been talking about the need to introduce observers in order to make sense of things like entanglement entropies in the context of quantum gravity. And so there's some parallel between what I talked about today and some deeper questions about the breakdowns of EFT and the need for observers when making sense of finite and divergent quantities. And so I think there's room to further explore these questions, and hopefully I've whetted your appetite for that. And hopefully I'll hear some more about that from you later, but thank you for your time. I'll answer your questions. Thomas, did I answer, are you satisfied? EFT in flat space.
I think so. Sometimes I'm dissatisfied. I'm trying to figure out what to ask next.
That's fine.
But I was a little confused actually for the flat space limit. So you interpret this as detectors that are completely localized at time, but there should also be an interpretation of detectors in flat space where the detector is infinitely far away and you just leave it on for a very long time. So where you really just focus on the IR, like
Sure.
the IR evolution of your state. And like you should be able to connect it to that, like try to avoid this UV problem. Like that you're saying like you're mixing like infinitely energy from the infinite energy insertion of the detector versus
So certainly we can start by taking, I mean, we could definitely try to recover the in-out correlators, which will have all that property by just taking all the detectors to be at different times, taking those times to be very far apart.
I'm saying to something else, like even in QFT, right, like the LHC collider, right?
Mhm.
You have also detector operators or like detectors that measure correlation functions between energy deposited at the LHC in direction 1 versus direction 2. Like these are well-defined like asymptotic observables that people can compute in QC and like compare the experiment there. So it's like, but they're not like local, right? Like,
No, they're definitely, everything is, all physical measurements in the bulk of space-time have some finite space-time volume. So it's really, so the issue is not that like, so again, when the point of those detector models was not to say this is the right way to think about what a real physical detector is. It's to say, if you calculate it, so for example, I should just say the calculation of in correlators in flat space is a thing that many people do all the time as a tool for understanding cosmological correlators. So those quantities have all of these funny properties. If I go and calculate the in correlator in flat space in an effective theory and I compare it to the one from the UV theory, I'll be missing all these terms. And people calculate those all the time. And they're not thinking of them as like, oh, but that's because I introduced a detector here and a detector there and they had too much resolution. They're just calculating an object that seems perfectly reasonable to calculate an EFT. Okay, and so the question is, the question we're trying to understand is to what, like, why are those things, like, how should you think of what can and can't happen for that object, which is the in correlator? And I'm giving you the detector to understand some of the unusual properties of that object. Right, that object contains production of particles from the vacuum. So, for example, when someone shows you one of these correlators in cosmology, it is conventional to say, see, this is because cosmology is in a time-evolving space-time, and so we produce particles from the vacuum, and you can see the particles have been produced from the vacuum because I have this two-point correlator of some field. And you say, and you tell some story about particle production. And then you calculate exactly the same thing in flat space, and you also find a non-zero answer. And so you say, well, why were you happy calling that particle production in de Sitter space because of the expansion of the universe, when in flat space, there's not particle production, it's time translation invariant system? And the answer is, well, it's just no confusion if you think of that object as being related to a physical detector. But so that's the motivation. It's not to say you should think about detectors this way. Of course, the right thing to do is to model the detector more physically for the system in question. It's just that in cosmology, this is the thing we calculate. Like, this is the quantity, and the importance of understanding how to like the role of EFT for these objects is important because we work sometimes directly with the wave function of the universe assigned at a single time. And to understand, for example, what is that? Can we describe all of cosmological EFTs with a wave function, or should we be working with a density matrix? That is a question that there's not a clear answer to that, even in the cosmological context for, say, doing something like calculating predictions from inflation.
So is it clear from the point of view of the low energy person? But these things are, it's a little bit unclear whether these things are low energy or not, but let's imagine you allow yourself to put, they're clear what the rules are for what kind of terms are allowed without calculating in lots of examples.
Yes, so it's clear, so the rules are pretty clear. They're local terms, the limit equals 0, and it's just a sum of operators. It's a bunch of local operators, but there can be time derivatives, is the only non-trivial. So otherwise, it looks like a bunch of fielder definitions if it wasn't for these time derivative operators. But and so there's just this unique, fairly small set of operators, and their behavior is pretty predictable. And that's the sense in which you can say it's always semi-local terms. Like, there's a one-to-one, you can just count all the possible things that can happen, and they're always reducible to semi-local terms or fielder definitions. So just those two possibilities. I think it also, I'm trying to remember, I just had I had a thought relevant to your other question, but now I'm blanking on what I was gonna say. Sorry, I just escaped my mind. Maybe we can let people go. I'm happy to stick around and answer the questions.
All right, let's thank Dan again.